So let me interrupt and just sort of check in on these two. Again, it seems either you're chugging along or you're doing a very good job of hiding your despair. But it seems like hopefully it's the former. So again, just to show that one more time, draw a picture always larger than you think you need. When you see a line like that's right, something like this, you're like, okay, I'm going to need to figure out the equation of that line. And I said, I know I'm going to have to do this both ways, so I'm going to invert that also. Y is a function of x is a function of y. And then I'm going to do y first. So I write the limits, and then I do y and x. I put the function in there, and I'm like, OK, what's happening with y? Where's y going from? Well, y starts from here, and it goes up to there. I often will just sort of draw that little arrow on. It can be really helpful. And so, I'm going to start at this function, and I'm going to want it in this form. This tells me what y value is as a function of x. So then in here, I'm allowed to have an x's. My y limits depend on x, right? My y limits depend on x. Different x values, I start at a different y value. And then x, in order, like if you imagined all of these orangish things, add up all of those orangish things, I'm going to have to go from 1 to 3. And then if you wanted to do it the other way, then we'll sort of be taking these blue steps, starting at 1 and going to the line. So x goes from 1 to this. So then when I'm done with this, I have no more x's. It's just in terms of y's. This x is the dummy variable that gets integrated away. This y is OK. And then I end up with an integral in terms of y. So this one is a little bit trickier, just because if you want to do the y integral first, you need to break it into two integrals. Because the function that defines the lower boundary of the region over which we're counting up rabbits changes here. So you do this piece and then that piece. And you can do that because integrals are just addition. Like I could add up all the rabbits in one dorm and then all the rabbits in another dorm, add them together, you get the total number of rabbits. All right. And then if you wanted to go this way first, now your upper and lower limits are both functions and not constants. Right, so different y values give you different starting values and ending values for x. And that's what happens here. If we decided we wanted to do this out, which I'm going to be pretty confident we don't right now, it would not be, I suspect they'll both be about the same amount of work. Even though this is two integrals, this is one integral where you're going to have junk above and below. So either way, it'll be 10 or 15 minutes of algebra or saying hi to a computer. OK, so now you are experts on counting up rabbits in triangular regions. But you probably can guess where this is headed. Sometimes rabbits don't live in triangles. Right, so and in general, in fact, it really could be anything that's sort of piecewise linear, right? You plug in a line, you figure out the equation of a line, you figure out what you have to do to the integrals, you draw some nice pictures. You can do the same thing with upper and lower limits that aren't lines. And that's what the next two problems are. So oh, that's interesting. Let me figure out what that should be in a second. So let's try problem 3. That should be x cubed. Yeah, that makes sense. So yeah, so let's try problem 3, and then I'll try problem 4, and then we'll increase our fun by 50% and go from double integrals to triple integrals. So we sketch our region of integration. And the picture now is that the density of rabbits is given by this function. We want to know the total rabbits in the circle. And so the equation of the circle, x squared plus y squared is r squared. If r is 2, then that's 4. And I'm going to need to solve this for y. So got that. Or you could solve it for x, I guess. I decided to integrate in the y direction first. So then, right, so y goes here, x goes there. Y, I notice I'm doing these orange things. I start at the lower part of the circle, and I go to the upper part of the circle. This branch of the circle is the negative root, and this is the positive root. And I'm getting different values. These values depend on x. If x is 0, I go to from +2 to -2. If x is 2, I don't go anywhere. So we get these fun limits. And then I need to add up all of these little orange strips from -2 to +2. Did anybody get a number for this? So let's think about this. So
x squared y over 2.
So this is, yeah. It's 0, yeah. Because it's an odd function in both x and y. And so you're going to have positive parts here, negative parts there that are going to cancel out. So there's one of the WebWork problems, I think, asks you to say without doing calculations if an integral is positive, negative, or 0. And you will all have an experience in your life, perhaps multiple ones, where you're on a roll, well, kind of like you guys were this morning. You seem to have pretty good energy. The storm is coming. We're going to do math. I don't know. But so you're going along, and you do this, and this probably wouldn't be that long to do. But maybe you spend 10, 15 minutes doing integral, and you get an answer, and it's 0, and you realize, I didn't need to do that integral. Yeah.
I was doing the one-on-one program yesterday, and the first thing I said that, well, it has to be 0, but it's still a surface, even though the values are negative and positive. So why don't we not take the absolute value and consider it?
OK, so I guess the rabbit story may have broken down a long time ago, but the rabbit story is really going to break down now. So if you had, maybe it would be better to think of it in terms of like charge density. So you can have positive charge and negative charge, and so like what's the total charge on the disk, for instance? It could easily be 0. The total number of rabbits, there really aren't negative rabbits. I mean, I'm not a biologist, but probably not. So yeah, if you think of it in terms of charge.
Okay.
Yeah. Yep.
Okay, now it makes sense.
Okay, good. Yeah, we left the rabbits. Yeah, negative rabbits aren't so good. So let's take a moment to set up the next problem. Oops, that's yesterday's sheet. That's also yesterday's sheet. Where are today's sheets? Yeah, so let's do 4, and then I'll say a little bit about volume integrals, and we'll do 5. So, OK, so this was this problem. And again, just a reminder, we're in Calc 2, or the equivalent, you calculated the area of this shape. Here we're doing something different. We're calculating the number of rabbits in this shape, or the total charge, or the average value of this function. So we're not just sort of adding up this area. We're integrating a function over that area. OK, so now, in theory, we know how to do any two-dimensional area. You just need to figure out what functions bound the area, and then write your integral carefully as an iterated integral in x and y. And we know how to deal with curves. So now we're ready to do this in 3D. And let me just say a little bit that we'll just do a few three-dimensional examples because they're conceptually not that different from this. They're just harder to see, harder to draw, and take an enormous amount of time to do. So, I sort of think of Calc 3 very much as a survey course. I'm trying to, not in a superficial way, but try to introduce you to a lot of math and not emphasize calculational details for every single thing along the way. And part of that is I think that the calculational details, some of these things can be so, not even hard, but just so involved to calculate that doing those calculations get in the way of thinking about what it is you're doing and what the math is in the first place. So we'll do a little bit with three-dimensional integrals. Another really common thing that I'll definitely cover, but I don't want to get bogged down in, is doing integrals in alternate coordinate systems. So polar and then cylindrical and spherical coordinates, which is a really, really common thing to do in physics and elsewhere. But again, I'm going to try not to get, we could spend 3 weeks on these topics, and I'm going to try not to. So let's talk about volume integrals in Cartesian coordinates today, and we'll do a little bit more of this tomorrow. And my thinking is to have you guys do a simple example, and then I'll end with a more complicated example. So, all right, so three-dimensional integrals. For short, rabbits break down here as well, not only because you can have negative rabbits, but again, I'm not a biologist, but rabbits don't really fly. So, all right, volume integrals. And so we might have some density, and maybe, so you could, I was thinking this morning, this could either be like butterflies, right, because they fly. You could have butterfly densities. And we want to know the total amount of butterflies in a room or something. This could also be like chemical concentration. This could be an electron wave function. Could be charge density across some object. So anyway, so this is sort of generic rho for density. So let's think about rho as x, y, z. Could be like butterflies. And if butterflies, if you really don't want to think about butterflies, you could just put anything else you wanted there that exists in space. So where would this come from? Well, suppose you want to know the total number of butterflies in a room, and it turns out that butterflies are not uniformly distributed. Some places are more butterfly friendly than others. And so this is not a constant function. It depends where you are. And so you'd like to just do density times volume to get your stuff, but you can't do that because density has to be constant, and it's not. So you break space up into smaller little cubes instead of squares. And so then this would be something like this. Rho x I y I z I. And so this expression has units of butterflies. Butterflies per meter cubed times meter cubed, you've got butterflies. And then this just means that add up all the butterflies. Or, again, add up all the charge, or add up all the wave function, which turns into probability. In any event, now we know how to count butterflies. And so how do you actually evaluate one of these things? It's the same thing. You turn it into an iterated integral, except now you're going to have to deal with a z direction and a x direction and a y direction. So it's sort of like, imagine we wanted to know the butterflies in this room. Well, I could stand here and count the ones, just look up, okay, how many butterflies there are, and then I could go over here, and then I could go over here, and maybe as I do that, at each point I could write on the floor how many butterflies, 7 butterflies, 8 butterflies, 4 butterflies, and so on. And then once I've integrated the z away, then it's like, aha, we are going to do this. It's a 2-dimensional integral. Now you have a carpet across which is written numbers of butterflies, and you can then add up those butterflies in the x direction, and then you'll need to add them up in the y direction, and you have the total number of butterflies. Or you could decide to do it in any other order you wanted. You could go x and y and then z. It's all up to you. So let's try problem 5. And I think this will be doable. So give that a try, and then I'll end with a more involved example, assuming nobody gets hurt on this one. So I think, well, are there questions on this? What I'd like to do is end with a different volume integral, and then on Friday we'll continue. We'll do maybe 1 or 2 more volume integrals, and then we'll let our coordinates be curvilinear. So this is an example that is, I think, similar to one in the book. Where do I want to start? Is it safe to erase this number at this point, or this? OK. When I was doing my Fulbright fellowship, I was teaching, and students, through really no fault of their own, had not great English skills. Because the country switched from French to English as a language of instruction like 3 years prior. And so that would be sort of the one time when they would, like, I could act out very easily. I would go, and they would all go, wait. But I would ask, if I asked them, can I erase the board, they wouldn't always know what I was asking. So anyway, it's a good thing about math that you can write, like this works in any language. That's one of the beauties of it. All right, so we're going to imagine integrating a density although we're not, this really doesn't even matter. We're not going to actually do the integral. We're just going to set it up. But so imagine charge density increases with altitude linearly. It's not a super realistic situation. Butterflies increase linearly as you go up in the sky. Atmospheric concentration decreases exponentially as you go up in the sky. But anyway, so imagine we've got this, and we want to know how much of this there is in a cone shaped as follows. So the region W, and so now the book uses W for the region. I think not wanting, like I would be inclined to use V because it's a volume, but there's a V there. Anyway, so they use W because it's, so region W equals this cone. So this is going to be z equals 3, and so this is a cone, and all of this is sort of given in still in the problem statement, that the slope is 1. So that the radius of the cone and z are the same value. So we've got this shape, and we want to know what the total amount of butterflies or charge inside this shape. So I'm going to integrate in the z direction first. And what is this? This is, I'll just keep this as this, for x, y, z. And I'm going to choose to go in the z direction first. Why am I doing that? Well, probably because then I can take advantage of this 3. I mean, you could decide to integrate this way, but I think this turns out to be a bit nicer. And so this orange strip, so it's like now instead of being in this room, I'm in some sort of weird conical room, and I'm sort of walking around in the conical room, hopefully with high stick shoes because this is pretty steep. And then I'm looking above me, and I'm recording the number of butterflies. So what would my upper limit be for that orange thing? That would be 3. And where do I start?
Oh, that's the square root of that strip.
Yeah. And so this says my starting value is different. As I sort of move around different x and y values, I'm going to have a different starting value. But my ending value is always the same. And the starting value is some z. And what do I want? I want z as a function of x and y, which is happily what we already have. So once we do this, now we just have a double integral to do. So I sort of picture, it's like we've taken this density and we're sort of like collapsed it down from 3D to 2D. I've added up everything that's above me. And so now I have an area density of butterflies instead of a volume density of butterflies. So another way to think about this is, OK, so I need to do this walk around the inside of a cone and count the butterflies above me and blah, blah, blah. Over what x and y values should I do that?
Negative square root of 9 minus x squared for positive.
Yes, that doesn't quite roll off the tongue, but right. So this is x squared plus y squared equals 9. So let's say x is 9 minus y squared square root. So let's do x next. So then I'm going to need to, let's see, I should maybe kind of color code these things. And then if I'm doing x, that's going to be my x. This is x, y. And y goes from -3 to 3. So I guess this then. So the picture here again is we're adding up butterflies in space. First, I'm going to do it in the z direction. And where I start depends on my x and y. And then, so maybe, sort of I'll do that. And then this says, oh, wait, but you've got to like do all of these x things, add up all these purple things once you've added up the orange things. Then you've got to add all those purple things, which themselves involve orange things. You would need to add up along here from -3 to +3, and you finally get all of your butterflies. So another way to picture this, so let's imagine you have a cone filled with butterflies. And let's imagine that's a little tough because the floor isn't there. So let's imagine all right, so this will take some imagination. So let's imagine something we put chloroform in the thing, and the butterflies all die, but because they're good butterflies, they all go to heaven. Okay. This is neither physically, biologically, nor theologically correct. So then you've got a whole bunch of butterflies on the ceiling, or like I sort of wanted it to be on the floor, but it's like, no, they're not on the floor. They're based sort of on the ceiling. And you want to like, how many butterflies are there? And so then you could say, all right, well, I'm gonna imagine there's just sort of like sitting in a circle or something. You have like boom, they collapse down. There's a circle of butterflies. Then you can imagine sort of like sweeping them all. So now all the butterflies are in a line. And then you could take that line and scoop up all of those, and then your answer is a number of butterflies. So anyway, so that's what this is. That's what this is doing. So we'll do a little more. We'll do one or two more examples like this in class. Again, you can kind of see how conceptually it's sort of. I think these are kind of fun brain teasers to think about. Actually doing this integral would just be a half hour, or maybe, I don't think it's worth doing too many of them. So we'll do a couple more examples like this, and then we'll look at curvilinear coordinates, which often make complicated integrals simple, even though it doesn't seem that way at first. So what time is it? I've got about 10 minutes before faculty meeting, so I'm happy to hang out and take a break if people have questions.